thank you again, Ray, for being with us. This is going to be a fascinating session. And if you are an engineer, if you are a professional race team, if you want to learn about aerodynamics, I don't think there is anybody more qualified than Ray to tell you about it, and also to do it in a very educational way. You know, I had the chance to meet with Ray many times over the years, and he has a very natural and easy way to explain the most difficult things, because he's a lot smarter than I am. He's a, you know, great engineer and a great brain. So Ray, I think it's 3:30 here in California. So Brad, I will hand it to you and you guys go.
All right, thank you very much, Francis. We appreciate that. And again, if you're just joining us, want to welcome you once again to Online Race Industry Week. My name is Brad Gilley with SiriusXM NASCAR Radio Performance Racing Network. Very happy to be hosting this session with Ray Leto. And just read a quick bio on you, Ray, and talk a little bit about what TotalSim is, and kind of let you take it away. And if folks have questions, they can do so in the chat as well. But Ray is a 25-plus year veteran of open wheel racing. He has a BS in aerospace engineering from Penn State, which he got in 1985. Began his career by working his way up through the motorsports ranks as a mechanic and an engineer. As a key member of Team Rahal, Leto spent 15 in many roles, including race engineer, aerodynamicist, chief range engineer, technical director, kart team manager, and general manager. And there's so much more about you as well, but an impressive resume for sure. But TotalSim is a computational fluid dynamics consulting and solutions provider, supplying expert insight to global clients in the automotive, motorsports, aerospace, process engineering, energy, and marine sectors. And basically, Ray, you guys, it says here on your product page on EPARTRADE, you take ideas from initial concepts to high performance reality by combining our real world engineering experience with advanced CFD technology, and you make it easy to accelerate design and development through automated CFD workflows and analysis and self-service applications. And I am hugely fascinated with what you guys do, and certainly look forward to hearing about it. So I know that's kind of the broad strokes, but tell us a little bit more about TotalSim.
Sure. Yeah, I've got I really appreciate first off, the introduction and being included in this. And Francis is way too kind with his compliments. It's part of his job, but it's really flattering. And thanks, Brad, for the great introduction. I think I'm going to try and share my screen, run through a quick presentation. One great thing about CFD is all the colorful pictures we can do. So I'll try and see if we can do that. Can you see my screen okay?
Yes, sir.
All right, great. So yeah, like you said, I'll give you a little bit of a background on ourselves and our company. We're motorsports people. TotalSim basically can trace its roots back to the late 90s when Adrian Reynard and Dr. Rob Lewis started Advantage CFD as part of Reynard, became part of BAR F1, which became Honda F1. And then in 2007, Rob took what was the outside consulting portion of that CFD core group, left some key guys with the F1 team, and took all the outside consulting and created TotalSim. Part of the outside consulting involved working with Honda here in Ohio at their R&D center. So Rob and I had talked about kind of branching out into the US and starting a company here as well. Since then, TotalSim now has an office in Japan. TotalSim in the UK has built several other businesses, Auto Research Partners that's developing a straight line testing facility, Silverstone Sports Engineering Hub that contains a cycling and Olympic sliding sport wind tunnel, very specific wind tunnel, a lot of CFD and work around that, and Vortec, which develops skin suits for mostly Olympic athletes. Here in the US, like you said in the introduction, I spent most of my career in IndyCar and Champ Car, mostly at Rahal, doing everything from race engineering. I was happy to see one of my race drivers on earlier. Brian Herter was a driver I worked with for 4 years at Rahal. So lots of wind tunnel testing, things like that. My business partner, Nathan Eagles, came out of the CFD side of things. He did some time in aerospace and then worked at Advantage CFD and BAR. Then he started the CFD department at Williams F1 and was there for a decade running that before we got together over here. So we have a diverse background in physical testing, wind tunnel testing, CFD. And so mostly what we do is aero development. Like you said, we get involved in all kinds of things. We've diversified from automotive and aerospace into all kinds of things: marine, Olympic sports, industry, anything that has gas, fluids, water. We can model it with computational fluid dynamics. We're doing a lot of general aviation and drone work as well. And that's fairly interesting, concentrated in our small office we have out in California. So we still get involved in some physical testing and a few other things as well, but our core business is trying to apply this motorsports mentality of quick product development to different industries and move people forward with that kind of mindset, which we find interestingly, for those of us who've been in motorsports our whole life, when we get out of it into other industries, things move pretty slow. So we try and change that. So what we want to talk about today quickly was basically what can we do with Aero Data and how do we get it? So there's, right now, most of us know that you can get data, on track or in a wind tunnel, either full scale or scale. Or now with computational fluid dynamics or CFD. So each of these things have different, pros and cons. They have different cost levels. Obviously, on track is the real car. You're out there, but you have to have good data acquisition. It's hard to get repeatable data. Maybe you go to a specific straight line testing facility to really hone in on getting data. During a race weekend, it's quite difficult. Full scale wind tunnel testing, again, it's the real car, but it costs what a real car costs. We got to build prototype parts. Full scale wind tunnel testing can range anywhere from, $500 an hour for a small tunnel to, $3,500 an hour or something like that. So very expensive endeavor. Scale model wind tunnel testing is great if you have a model and you have access to it. If there's a model you can rent that simulates your car, that's great too. But if you have to start from scratch, quite expensive. CFD is somewhere in between. We've got, there's barriers to entry there too. So you need experts, you need 3D geometry. We need to get that car from the physical world into the virtual world. But these are what people are doing today, top level motorsports. And we see this moving down into the lower series right now. So what can we do with Aero Data? Why do we do it? Well, my big thing is getting people to understand what they have and optimize it. So it's not so much always going out and trying to invent something new or design a new part or design your way out of a problem. Sometimes just optimizing what you have can move you to the front of the grid or move you up the grid substantially. So you have to understand that first. And that's just like, let's say your dampers or your engine, your transmission. You're going to go to a shock dyno, you're going to understand that. We're going to go, on an engine dyno or chassis dyno and understand where we are with our mapping and things like that. Same thing for aero. We want to go and just characterize the car, understand where it is. Then we can go, like the next presentation, Danny Newland will tell you for sure, is that once you have these maps for these things, then you want to go and find out what your trade-offs are. How can we optimize it? So we're going to find out that these maps that we get maybe tell us to run one thing at one track, something else at another one. So we're definitely going to have different trade-offs for L over D between, a street course at St. Petersburg or a speedway at Daytona. These are, even if you're running the same car, your trade-offs and your optimization. I threw up a couple of color plots here that I thought were really cool. One of the kids at Ohio State University that's running the aero department or the aero side of their Formula SAE thing, Matt Kronheimer, did some nice plots, which illustrates what I think is, a race engineering here, and trying to look at trade-off plots of what would happen. This is L over D curves versus lap time for them. And as you make your way up through these contour plots, you can prove that you're making the car better. And you can do this virtually before you even go to the racetrack. So, that's what we want. That's what we want to do with Aero Data. Whether we go to the wind tunnel or we go to CFD, we want to map it. So we're going to, with a typical car, let's say like this F3 car we've got here, you would be mapping a range of ride heights, yaw, different attitudes, and then building that base map that we could then feed into something like Danny's chassis sim or something and look at these trade-off studies and do some optimization and say, where are we running our front ride height? Could we do better by changing the pitch of the car and optimize through the middle of the corner that downforce, or down the straight and minimize the drag, things like that. So what is CFD? Basically, what are we talking about here? So really, CFD is actually just a virtual wind tunnel, essentially. So we're taking a 3D model of the car, moving it into a virtual world, and then we're using physics and math to solve the fluid flow around it, solve the forces on the vehicle, and then better understand it. So it involves going through a process of taking 3D geometry, what we call meshing, cleaning it up, building that volume of fluid around it, and then solving a bunch of math on a supercomputer. So the barriers to entry here are getting that 3D geometry into the virtual world. Do we have CAD? Do we need to do a scan? You do need some expertise in this. This is not picking up you know, some app on your phone and learning how to use it in a few days. There is a lot of expertise that goes into it. And then of course you need the software and you need hardware. I mean, typically for these top end programs, we tend to solve our cases on somewhere between 200 and 400 cores per case. So this is a true supercomputer. And we're fortunate in the fact that we have a couple thousand cores in-house. We have a fiber connection to a supercomputer center here in Central Ohio that's one of the best in the country. So we have access to thousands and thousands of cores. And each of those cores typically costs about 5 cents per hour to rent or operate. So not a cheap exercise, but again, keep it in perspective with running the real race car. So what extra can CFD do versus going to the wind tunnel or the racetrack? One thing is the flow visualization. We can see what's going on. We can cut through the fluid. We can color it. We can look at the flow on the surface. We can do optimization. So we can try many, many, many things in the virtual world that cost us a lot less than building prototypes and going to the racetrack. Then we can do things that we can't do on the racetrack or even in the wind tunnel, especially in the wind tunnel. High yaw angles like this dirt late model that we've got a picture of here that we work with a guy named Matt Furman on this model. He's a CAD guy, works for Siemens, so he drew a great model and we did some interesting stuff. 15-degree yaw angle is not something you can do in any full-scale wind tunnel these days, and that's what these things run at all the time. So why would you be testing something at an attitude or a situation that you're not actually going to see in real life? Some other things are doing traffic. So this middle plot, we've got a picture of what happens around for instance, a cup type car here where when there's interaction between cars. So we can't do that in a wind tunnel, have more than one car. Curve flow it's an interesting thing in the fact that when a car is going through a corner, it's not the same as testing at a slight yaw angle. The flow is actually curved. The car is taking a curved trajectory. So that's something that you can do in computational world that you can't do in a wind tunnel. So those are some interesting things. So obviously one of the best things is visualization. We typically run hundreds and hundreds of movies and pictures on every case we run so that we can compare them. So you can really explore what's going on. This obviously from the real world, having a smoke wand or kind of, that would be analogous to that, or putting tufts on the car. But we can do this over and over again in the computer. Another thing is optimization. So we can morph and bend shapes like it's clay or you know, a pliable material, and then set up basically a study that's called a design of experiments type study, where you parameterize the geometry in a way that you think you can control it. And then we take basically a shotgun approach to it. And it's almost like a Monte Carlo or whatever, where we're just going to roll the dice and try every single permutation and combination, come up with a huge scatter plot and find out that front of L over D that increases our performance. So I wanted to just give a couple examples of types of engagements that we see in the industry these days or over the last few decades, and how that's changing. And we've had, you know, large scale engagements with like factory type racing programs and original equipment manufacturers for their factory type work. Those are large scale things that are over hundreds of thousands of dollars a year. We do see some medium scale things, which could be from a top level professional racing team or other organization that's interested in this type of stuff. And then smaller scale stuff. And we're seeing a lot more of this at a lower scale or lower tier racing where people have interest in finding this information. And most of those projects are 10,000 or under. Then we've also been supporting DIY type things where people have some experience in this, or they've done projects with us, then they want to start doing it themselves. So, a large scale project would be something like our engagement with Honda. We've worked on and off with Honda Racing since this company started, and we've done things like Aero kit stuff for IndyCar and whatnot. These are big, large projects that akin to Formula One or something, where we're designing an entire program from scratch. And these are obviously kind of sky the limit type things. Same thing in Cup. We were fortunate to be involved with one of the OEs back in 2013 when the new Gen 6 came around. Really cool application of CFD in a design process where you can start giving design cues. There were stylists involved, so because there's supposed to be brand cues on these type of cars. So you want to give feedback to those designers so that they're, not hurting the performance of the car, but still keeping that character that they wanted in it. And that was all done in kind of a virtual world before real prototypes were built and clay models were done. A medium scale project. We've been at TotalSim, we've been working with iRacing for most of our existence here, 8 or 10 years. And if you think about it, it's a perfect application for, a virtual racing. Putting a car in a virtual wind tunnel is perfect, right? So we've taken, when they came out with their dirt over a year ago, we did a lot of work with them to develop aero maps of these cars. And this goes back to the first slide I was talking about, the uses of Aero Data. We have to characterize the car to be able to simulate it. And in particular, this type of engagement is perfect because there's no known data for some of these cars. So, but they have 3D geometry and they have a need to understand the physics and how the car reacts. And we got really good feedback on that. Recently, we just worked on their new USF 2000 and Pro 2000 cars, full mapping on that stuff. Smaller scale projects. We've done a lot of land speed cars where, somebody's got a particular small problem or they want to check stability on the salt flats. What's the car like if it gets out of shape? Some of these have come with CAD data. Alan Johnson, those guys have supplied CAD. Other people, it's a scanning project where we have to go out and scan the real car and then throw it in the virtual world. So that kind of brings us to the how do you get that 3D data? And if you don't have it anymore, there's people out there that can reverse engineer or scan the car. We're one of them. There's lots of vendors out there doing it, and they do it really well, where you can take exactly what you've got in short order, and for several $1,000s, you can basically create a full CAD model of your car, and then we can push that right into the virtual world. And then the DIY side. So we develop our own software, which is an open source software. It's a variant of an open source project that's out there that's been specified for or specifically altered to work better, or how we feel it should work in the motorsports and automotive world. And we have worked with people. We have this installed at major original equipment manufacturers, large auto companies that use it for their drag prediction. So once we've worked with somebody, we can kind of help them set up their own CFD department, train them how to do things. One good example of that is NASCAR itself. NASCAR R&D uses our setup, and Eric Jacuzzi there in his aero department has used our software. We don't see any of the results. They do all their own work. They do multi-car work. They do design work. So the genesis for this new, a lot of the aerodynamic design on the new car that's coming up in, well, I say 21, it's 22 now, thanks to 2020. But yeah, so that's a good example of how we've worked with someone and then kind of set them off on their own to expand. We've got a new option too, where we've got kind of like a a TurboTax kind of way of doing things, that if you kind of click your way through a web interface, and if you are a team or a manufacturer that is in control of their 3D CAD, we have a way now where you can upload all that. It has all of our best practice in the background in a black box that we've exposed a little bit of, but basically you can focus on being a designer, not have to worry about being a CFD expert, and get all this post-processing and data back, and treat it like a real virtual wind tunnel. Upload your geometry, get the data back, just like you would go into the wind tunnel. And then we display all the results in what we've called a results tool. So it makes it easier to analyze and look at things. Anyway, that was my short presentation, Brad, and hopefully I educated some people on what's going on out there in the CFD and Aero world, and maybe we've come up with some questions or something that someone has.
Yeah, a couple of things from the chat. Let's see. Steve Shelley just says, hang on, I lost, there we go. Great to see Ray. First met him in 1987 when he was prepping Carroll Smith's son's Super V. He was a genius then too.
Man, this is what I came for, is all the compliments from Francisca in the audience. I didn't see the audience, I swear.
That's funny. A couple real questions. It says, Ray, remind me, do you use Sculptor? And that was from Paul Glessner.
Yeah, well, we used to use Sculptor. And we still do on occasion. Sculptor, thanks for the question, Paul, is a specific software that you use to manipulate CAD. So you can say, take your initial design and then treat it like it was clay and morph it and push it and pull it. And then you can do that in a structured way where you can set up like I was showing with the optimization, where we can push and pull that. And there's more than one type of software that do that. Sculptor is one of the originals, and they're still very good at it. There's others like ANSA from Beta CAE, and even some native CAD software has that ability now to push and pull, just like you would in the wind tunnel, banging on a piece of metal or scraping on a piece of clay.
Okay. Derek Dixon wants to know if the PowerPoint would be available if someone were to request it.
Yeah, I think we can do that. There's a few things in there that I might have to blur out, but yeah, and we've got some info like that on our website, and you've maybe spurred me to actually just post it up there.
Okay. And then Tarek, I can't see the full name here, said, how important is validation of your computations, and how is that generally done?
Well, it's a big deal, because just like anything else, you have to kind of have some anchor in reality, right? So you can't just go off and make a model and then assume it's correct. You have to have some anchor. So, for us, having a couple decades in doing this, we've developed our process based on trying to get it to correlate. And we feel pretty confident that our best practice can go straight to the racetrack. But nonetheless, we're always constantly looking at that. So if we have the opportunity to work with a top-level team or an OE and go to a full-scale wind tunnel like wind shear, where we're running the real car on a rolling road, we do a lot of correlation with that. Aside from that, going out and just trying to correlate to the to straight line data or on track data is possible as well. And I think Danny in the next segment might even talk about some of that. That's a lot of how he builds his simulations too, is like that correlation exercise, or reverse engineering that information from the data that's available to you. But it's really important. And I think the other point to make there too is that if you go test a straight line, you go to wind shear, maybe you do a scale model test and you do a CFD, each one of those things gives you completely different answers sometimes. And usually for good reasons. The physics is not always the same in all these places. And there's compromises that are made. And when you're in a scale tunnel or versus a full scale, these things are for very good reasons going to give you slightly different numbers. So sometimes, more data is more confusion. So you always have to have that kind of bridge to understand that, and get comfortable with yeah, I kind of understand the offset between CFD and my on-track data or my wind shear data or whatever it is. And then just make sure that you understand it so you can continually progress your designs forward with confidence. But yeah, it's a constant battle.
Well, Ray, I have to say one thing I think you've definitely shown with your presentation is, number one, you can describe this in a way that just about anybody can understand. But
Well,
number two, the efficiencies in time, in cost, it's quickly learning if something is not right, versus actually building something to figure out it's right, just seem incredible and would be a huge asset to any race team out there.
Yeah, I think that's a good point, Brad. We see going forward that more and more this virtual prototyping is the way big industry is going to take more whacks at it before you build that first prototype and hit the ground with what your best guess is right to start with.
Yeah, well, I do want to remind folks they can go to EPARTRADE.com, sign up if you haven't. It just takes a couple of minutes. You can go to the product page for TotalSim as well and just literally request information from them directly from there, and would encourage you to do that. But what an amazing presentation. Really appreciate that.